Hello everyone. Few of you wanted me to make a video for the exam 3 practice questions. So let's go ahead and do that. So the first one wrote the enol tautomers of the following ketone. So what you are seeing right now is the keto form. So the enol form is the alpha carbon having alpha hydrogen can be removed, let's say like this. So you have a base. So the base comes and grab this hydrogen and then gives its electrons to this carbon. You can also form a double bond. Let me go ahead and draw this one again. Here, let's say you have this and hydrogen will be removed. So it's going to form a pi bond, and then the pi bond between the carbon and oxygen opens up. So you will have a molecule like this. So you form the double bond right there. So then this oxide, alkoxide and ion can be protonated, maybe from a water molecule, to give you the enol form. The enol form like this. OH, double bond, like this. So this is one of the enol, and if the hydrogen that's on this carbon is removed, you will get the other enol, which is going to be double bond OH like this. So these are the two possible enols, enol tautomers. So when it says draw the enol tautomer, so this is the keto form and these two are the enol forms. Okay. And then the next one, you can also see the answers towards the end of this handout. Draw the most stable enol tautomer of the following ketone. So you have seen when we draw the enol, it has the ene, alkene. So we can also consider the most stable enol. Just like we would see what would be the most stable alkene. So these are the two possible enols. So this is one, that is if you form the enol with this carbonyl group, and then the other one would be this OH, this, right? So if you consider this ene part, so this has ethyl group, right? And whereas here what you have, this is a methyl group that you have in that ene, and then here you have a ethyl group. So if you look at the alkene part, which one is going to be more stable? Alkene. So both alkenes are tri-substituted, 1 2 3 1 2 3, but this one has a alkyl group as ethyl group, making this alkene most stable. Okay, so the most stable enol tautomer would be the second one. And then the number 3, because we have learned about the alkene stability in organic 1 also, the more substituents would make it more stable. And then ethyl is a bigger substituent compared to the methyl. Draw the product of the following reaction. So this one, I think the name of this reaction is HVZ reaction, where when you have a carboxylic group and you have alpha hydrogen, that can be replaced by bromine. So this is in our lecture notes. So you will get this product CH2, and then the alpha carbon having alpha hydrogens, so this is COOH. So one of the hydrogens will be replaced by bromine. And you also have the mechanism how this happens in, if you want I can show you what would be the slide number. Let me try that one. I think it's HVZ reaction. Yes, HBZ reaction, which is the Hell-Walhart-Zelinsky reaction. You can see this in slide 18, and also you can see that it replaces the alpha hydrogen of a carboxylic acid by bromine or bromide. And you can also see the mechanism how it happens in slide 19. Okay, so that's the answer for that one. And the next one, draw the iminium salt that is formed in the reaction shown below. The iminium salt. So how do you find the iminium salt for this one? What would be the iminium salt? Okay, so this one, this is what's going to happen. So you have this molecule right here. So you have a lone pair on the nitrogen. So that is going to form a double bond right there. So then the double bond that already have in the cyclohexene ring goes and attack the methyl group and leaves iodide group. So the resulting molecule would look like this. You have a double bonded nitrogen, has two methyl groups. Since nitrogen has 4 bonds, it would be positively charged. And then the carbon, where you had the double bond, have your methyl group attached to that. And then the double bond in the cyclohexene ring is no longer there. Okay, so that is the iminium salt. The next one, draw the product of the following reaction. LDA, lithium diisopropyl amide. Again, the cyano group, you can consider that as a carbonyl group, right? Because carbon and nitrogen act as a carbonyl group, C triple bonded to N, similar to C double bonded to oxygen. So there are 2 hydrogens here that makes it acidic. Because once the one of the hydrogens are lost, carbon ion can be resonance stabilized through the nitrile, which is a CN group. So when the LDA, which is a lithium diisopropyl amide acting as a base, go and take one of these hydrogens and form a negative charge right there. Okay, so I'm going to go ahead and draw what we will be getting after removal of the hydrogen. We will have a 1 hydrogen there and a negative charge. So then this is a carbon ion can go and react with ethyl iodide, ethyl part, and removing, this is supposed to be an arrow, removing the iodide group. So as a result, your product would be CN, and here you will have a ethyl group attached to that carbon next to the nitrile group, which is the alpha carbon. Okay, and then the number 6, draw the product of the following reaction. Again, similar to the previous one, there are 4 hydrogens over here. There are 2 alpha carbons, and each alpha carbon carries alpha hydrogens. So the lithium diisopropyl amide again will remove one of these hydrogens and form a negative charge over here, and then it will react with ethyl iodide. Iodide would be lost, and then we will have this molecule, ethyl group attached to that alpha carbon. Okay, that is the product. And then the next one, again similar to that, right? Same thing, same reaction. So you will be losing the hydrogen. There are 2 hydrogens. You will be lost 1 hydrogen, LDA base, and then it would react with this guy, right? So once it react with propyl iodide, propyl group will be added at that carbon ion, which is the alpha carbon. So your product would be there for the propyl group will be added over here. 1, 2, 3, like that. Okay. And then the next one, fill in the empty boxes. Again we have LDA, LDA with a nitrile. Remember in a previous question also, nitrile group can be considered as a carbonyl group, right? So then you can consider that it has a alpha hydrogen. So LDA will remove one of the hydrogens from the alpha carbon and create a negative charge once the one of the alpha hydrogens lost. So then it's going to react with the methyl group and leaving iodide. So you will have your nitrile group CN, and then the carbon, and then you have a methyl group right there. Okay, and then you add sodium borohydride and water. What's going to happen to nitrile group, CN group, with sodium borohydride? So we learned that sodium borohydride is a reducing agent that would reduce CN or the nitrile group to CH2NH2. Okay, so your product therefore going to be like this, and then this carbon in the nitrile group will be CH2, and then the N would be NH2, like that. And then the next one also similar, LDA ethyl iodide. Again LDA will grab the hydrogen from the alpha carbon and will react with ethyl iodide. So you will have this product ETO, ethoxide, over here O, and on this carbon you have a ethyl group, right? And then you add sodium borohydride and water. Now we have two groups. So we have a ester functional group, and you also have a aldehyde functional group. Remember, sodium borohydride is a milder reducing agent. It would not reduce ester group, but it will only reduce the aldehyde. Aldehyde will reduce to give you a primary alcohol. So your product would be there for ethyl group, oxygen. Your ester group will remain intact, nothing will happen, but the aldehyde will become a primary alcohol. Okay, so the next question also similar to this one. Number 10. So it's asking what is happening here. LDA ethyl iodide, which is the same like the previous one. So your answer for the first part is going to be similar to the previous one, right? And then you are getting this product, right? So once you get this the structure right here, you want this one, meaning your aldehyde also has reduced to alcohol, and your ester part in this molecule, I will draw it again. Ester and the aldehyde both had been reduced to alcohols. You see, ester part also reduced to alcohol. So what would be a reagent that we can use to reduce both ester and the aldehyde to alcohols? There should be a stronger reducing agent. So in this case, that would be then lithium aluminum hydride. You will use lithium aluminum hydride, and in the second step you will use water, okay, to get the alcohol. Number 11, draw the product of the following reaction. So you are going to react this enamine with acid chloride. Okay, propanol chloride. So what are we going to do here? Again, we are going to react this one like this. So the nitrogen has a lone pair. It's going to form a double bond. So then the double bond that you already have going to react with the carbonyl group of the acid chloride. Okay, so you can, there's going to be few steps going to happen here. I'm going to expand the carbonyl group. So the first thing that is going to happen is once it attacks the carbonyl group, carbon oxygen pi bond will open up and form O minus. Once the carbonyl group O minus oxide ion forms, so in the secondary step, I will do everything on this one, but it has to happen stepwise. Okay, the next step, O minus will reform the carbonyl group, carbonyl bond, and it leaves the chloride. So few steps I did in one structure, but you got the idea. So the product that you're gonna form going to be something like this. The double bond there, and on this carbon you have the carbonyl group, and there are two more carbons, 1 2, right? So this is going to be the product after the addition of the propanol group onto the this carbon. So the secondary step, you are adding acidic water. So when you add the acidic water, we have learned in the lecture that you can hydrolyze the imine group excuse me excuse me, back to the carbonyl group. Remember, what we have here is an imine group that is formed between a carbonyl group and secondary amine. So by hydrolyzing with hydronium ion OH3O plus, we can get back to our ketone, which is going to be like this. And you can find the mechanism for this one in your lecture notes. Excuse me. Okay, so that's going to be your product. You can redraw it like this to make it nicer. And on this carbon you have a methyl group, and then I'm going to redraw it, okay, like this. Okay, that's what you're going to be getting. And then the number 12, fill in the empty boxes. Again you have ketone, and then you have made an enamine. So ketone will make an enamine with a secondary amine, and you can identify your secondary amine going to be that molecule right there, H. And you can do it in the presence of a acidic medium. Ketone and secondary amine form enamine. Once the enamine formed, you want to make this molecule that is shown to you, right? So meaning at this position you have added this group, right? Remember in the previous one we saw in this one enamine that you can react with the carbonyl group. Okay, so similarly enamine here is going to react to form the aldehyde given. So what would be the appropriate aldehyde that we want? So it's going to happen like a conjugate addition. So if you basically break this molecule, like if you look at the way that we're going to work in retrosynthetic analysis, so that is the new bond that we are going to form, right? So we can consider, so we start with a portion like this. Okay, so then what we can do is you're going to react this molecule, this one, with this molecule, which is this. So the double lone pair of the nitrogen form carbon nitrogen double bond. So the double bond here going to react with the double bond. So this is like a 1,4 addition, Michael addition. So this will give you the molecule like this. You will have a molecule like this. Nitrogen, and it has this group right there. This would be now positively charged. On this carbon you will have this 1, 2, 3. 1, 2, 3 carbons. 1, 2, 3, O minus. Right, so the double bond, you're going to be attacking the double bond 1,4 addition. So it's going to form a double bond right there, which is the enolate anion. Once the enolate anion forms, it can reform the keto form. Okay, enolate form can go back to the keto form, which is this. Keto form, ketoenol tautomerism. Okay, and once this is being formed, and in the last step when you add HCl and water, so this is step 1, you get this product, and in the second step when you add acid and water, you can basically hydrolyze the imine salt back to the keto form, which is the product right here that is drawn right there. Okay, so in that step you will remove this part over here. That is the explanation for that. And then the next one, number 13, draw the product of the following reaction. What are we doing here for number 13? Again, so you have this anhydride right there. Okay, so if you expand this, this would look like this. So you have a CH2 group, and then you have COO, CH3, O, CH3. Like this. So when you add a base, sodium methoxide, so there are 2 hydrogens here. So one of these hydrogen can be lost, can be taken and form the anion over here. Once the anion is formed, this can react with this guy. Like this is going to attack that carbon, and it continues because it's all conjugated. Okay, so the resulting molecule would be then O minus double bond, and then the carbon here, O methyl, like that. And then once this is being formed, this is the enol form that I have drawn here, and then it can go back to the keto form. Okay, so your keto form would be I'm going to redraw it in the same molecule. This is the enol form. The keto form would be this form. Now sodium methoxide is a good base, and remember we still have one hydrogen there, and that hydrogen in the presence of the methoxide, it will grab this hydrogen and also makes it a negative charge. Okay, I'm going to go ahead and draw it in the same molecule. What happens? I'm going to form this. Since having two acetate group, two ester groups on the either side, and then you have a hydrogen in the middle, that hydrogen has a very acidic pKa, making it easy for the methoxide to grab it and form the anion. Okay, so if it said it's just one equivalent of sodium methoxide, we could leave it without creating the negative ion, but since it did not tell us that it has one equivalent, when you have excess of base, it basically give you that anion. Okay, so that's the product for that one. And then the number 14, draw the product of the following reaction. What you are doing here is, okay, you have a ketone with an alpha hydrogen, and then you are reacting this with in the presence of hydroxide and water, and you are also heating it up. So what kind of a reaction is this? This is the aldol reaction. Aldol reactions, so you can react the molecule with itself in the aldol reactions. Okay, so basically the base, so there are three hydrogens, excuse me, the base is going to take one of these hydrogens and create CH2 minus, and this has three groups. So in the aldol reaction, so this can react with another molecule of the same kind, and this is going to go and react with the carbonyl group of the other ketone, forming a bond between carbon of the carbon ion and the carbonyl group of the other molecule, giving you this product CH2, and then the newly form carbon, so in this CH2 right there, and then you form O minus. Okay, and on this carbon you have a CH3 group. CH3 group, right? Remember this carbon carry this methyl group right there. This is the one over here. So we are heating this up. So heating means it can also lose a water molecule. So once the O minus is being formed, it would grab a proton from the water and form OH. Okay, so this one can be lost a water molecule to give you alpha beta unsaturated product, which is this as the final product, alpha beta unsaturated carbonyl group. So this is your alpha, this is beta once the water molecule is lost. So with the heating, it will go all the way to give you aldol product and then the alpha beta unsaturated ketone. Okay, that's the answer for that one. And then the next one also look like aldol reaction. Now the aldol is going to happen between two different carbonyl groups. Now the first one does not have any alpha hydrogens. So then when the base is added, it's going to grab the hydrogen from this molecule. Okay, so the base will come, grab this hydrogen, form carbanion there. Okay, that's the first step. And then once the one of the hydrogens lost, you're going to be creating a negative charge. Remember, now you have only one hydrogen there. So then, just like we did it in the previous one, the carbanion will react with the carbonyl group of the other molecule and form a new bond between the two molecules. So this will be O minus, and then you have carbon, that newly joined one, COH, and then this carbon has two groups, so ethyl group, like that, right? So then once the oxide is been formed, it can grab a proton from the water and form OH group right there. Since we are heating in the presence of an acid, so this would further complete. So there is a hydrogen in this carbon, so this can lose a water molecule. Okay, so this OH group can be first protonated. Since we are doing it, the second step is done under the acidic medium, so this OH group can be protonated first, and then it can lose. So then the hydrogen will remove from the neighboring carbon the alpha hydrogen and form alpha beta unsaturated product, like this. Oh, I think I skipped 15, didn't I? I'll go back. So this is 16. Okay, so that's the product for that. All right, I think I didn't do number 15. You guys didn't even tell me. Good that I noticed it. 15. Draw the product that is formed when 4-methylhexanal undergoes an aldol condensation. I guess you know how to do this now already, since we did a couple of aldol reactions. I'll go ahead and erase this one. 4-methylhexanal. So what is 4-methylhexanal? 4-methylhexanal. Let's go ahead and draw it. So it's a carbon with 4 methyl. On the fourth carbon you have a methyl group, and then hexanal means 6 carbons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Hexanal. This is reacting with itself over here. Right now, you know, we are looking at number 15. Okay. So if you consider that you are going to make the enolate in this one, there are 2 hydrogen. Once the 1 hydrogen lost, carbanion can be formed here, and this is going to react with this carbonyl group and form a new bond. Okay, so you can draw this one. This carbon, you have other group. This one. So if you feel like you are losing the count for the carbon, you can start numbering them. If you number them, you can consider this as number 1, 2, 3, 4, 5, 6. So the carbon ion here, this guy is over here, going to combine with this one carbon, that is like this, O minus. 1, 2, 3, 4. So the fourth one has the methyl group 5, 6. So this will form the alcohol OH. Okay. And then in the next step would be removal of the water molecule. So to remove the water molecule, you have a hydrogen here. If it is happening in the basic medium, base can come, grab this hydrogen, give its electrons to form a bond and lose hydroxide, meaning a water molecule. So your final product would be like this. Self-condensation of 4-methyl cyclohexanal. Not cyclo, 4-methylhexanal. Okay. 1, 2, 3, 4, 5. I think I got the number of carbons correct. All right. Okay, so that was number 15. We did number 16. Okay, we did number 16. So let's do number 17. I think I'll stop this video here and then we can start the other one from 17 because it involves Claisen. So we'll start fresh in the other video. Okay, bye.